xem người ta có một con
để tay à? Ui, cái gì tao không hiểu.
là không tháo.
Good morning. We continue with chapter 12 of kinetics, and it seemed that I had forgotten to upload chapter 12. I just did it, send it to teaching assistant, and it will be distributed to the group. So thanks for pointing that out. Now, in our discussion about kinetics, one thing that kinetics are good for is getting information on the reaction mechanism. What is happening during the reaction? What is reacting with what at which time? And we can do that by looking at the order of the reaction, the dependence on the kinetics of which reaction. And you might remember we had looked at one particular reaction where there was oxidation of iodides with hydrogen peroxide in an acidic medium. And we saw that it's dependent of the hydrogen peroxide concentration, the iodide concentration, but not the acid concentration. And this can be rationalized by assuming that actually we have several steps during this reaction, and these steps each are like the collision of two particles together, or it could also be in some cases one particle collides with solvent and falls apart in that way. That is also possible. So these individual steps of the reaction are called elementary reactions. And so here you see, in fact, the global reaction of oxidation of iodide with hydrogen peroxide in acidic medium might be split up in 5 different elementary steps. And the first step, in fact, is the one where hydrogen peroxide and iodide are coming together, and they are generating hypoiodides and water. This hypoiodide is not one of the products, it's an intermediate. And in the second step, the hypoiodide is protonated and forms hypoiodide hypoiodous acid. This hypoiodous acid is a strong oxidant and oxidizes iodine. And it forms iodine. This iodine in step 5 combines with iodides, triiodides. Also in step 4, the protons are neutralized to water. If you add up all these 5 steps, you will get the global reaction. And you will see that in this global reaction, actually, there is no hypoiodide, there is no iodine, and so these all are falling away during the reaction. And now it will be based on which step is the slowest of knowing what is going to be the kinetics of the reaction globally. And you can consider this like being in traffic with your car. The speed of the traffic is actually caused by the slowest car. The slowest car holds up the rest of the traffic. So it's the same thing here. The slowest reaction is going to determine the rate of the reaction. And we call this slowest step the rate determining step. And in this case, actually, the first step is the rate determining step. And this is the car in front of the queue, you could say. So that means the concentrations of the reagents, hydrogen peroxide and iodide, will be important because they come together in that first rate determining step. And in this context, we can talk about the molecularity of the reaction. And these are the amount of particles that are coming together in the rate determining step. You could have a unimolecular reaction, and that means only one reagent is going to be involved. And you could also have a bimolecular reaction, which is maybe the most common, that 2 of the reagents are coming together. Now, in a unimolecular reaction, you might wonder, how do we get energy if there is actually only one particle? How do we get collisions? Well, in that case, the energy might come from any other molecule, like a solvent molecule, which is moving and giving its kinetic energy to the reagent without actually reacting with it. In the bimolecular reaction, of course, we don't have that problem, so it might be just through the kinetic energy of combined, the 2 particles combined, that we are getting above the activation energy. Bimolecular reactions actually are agreeing and matching with reactions of second order, because 2 concentration terms are important for such a reaction. So often one reaction is followed by another, and then maybe another, and so on. So reactions operate in chain. Several elementary reactions are working together. And this may involve so-called intermediates, which are not isolated. These are not the final products, but they have a task during the elementary steps that lead to the final product. In the previous slides you saw we have, for instance, hypoiodides, and so we have iodine 2. These are intermediates in the pathway of the reaction. And for instance, a typical chain process is known from organic chemistry. For instance, it's a radical process. Radicals are highly reactive. Intermediates are not isolated, but they are important for the reaction mechanism. And then the first step of such a reaction is to generate the high energy intermediate. if you look at the profile of the energy, such intermediates will be high up in the reaction profile. This is also why they are not isolated, they are not stable. So the first step is generating such reactive intermediates, and you could call that the initiation step. Now, in the next steps, actually there will be a so-called propagation. The reaction is going further, and these intermediates are going on to form products. They might form new intermediates, which react further and so on, and these intermediates react further. So now the reaction is propagating, meaning going on. So these are propagation steps. Then, in the last step, the intermediate might disappear. So now our reaction is stopping. This is a termination step of the reaction. For instance, if it is a radical reaction, two radicals are coming together to form a bond. Now our reaction is dead. There are no further reactive intermediates. So, one example here is the bromination of hydrogen, the reaction of dihydrogen to dibromine to form two molecules of HBr. Now, in our first step, the initiation step, we generate bromine atoms from dibromine, we could also say bromine radicals. This requires an initial investment of energy, because we have to break the bromine-bromine bond in dibromine. But this is relatively easy because that's a weak bond. Then in the propagation, the bromine atoms or the bromine radicals react with dihydrogen in the first step. This creates a stable molecule, HBr, but one of the two hydrogens is left behind as an atom or a radical of hydrogen. So that's a typical propagation step. You start from a radical and you get another radical. You start from an intermediate, you get another intermediate. In the second propagation step, the hydrogen radical reacts with Br2. Another molecule of HBr is formed, and a new bromine radical. So we are back where we started. We started with a bromine radical in the first propagation step. After the second propagation step, we have another bromine radical. So we can start all over again and again and again and again. Now, in the termination, this is mostly unwanted because it stops the reaction. The two bromine radicals come together, which is the opposite of the initiation reaction. Or two hydrogens might come together, and then we have dihydrogen. Or hydrogen and bromine come together, and then we have another molecule of HBr. Overall, the reaction is going to be that dihydrogen and dibromine form two HBr molecules, which is the result of repeating and repeating the propagation reaction. Here we have one from organic chemistry, the halogenation of methane. The same thing. So first, chlorine is split into radicals. Then the radicals add, and you see this is typical for organic chemistry, that you write the arrows in half arrows to indicate that you have radical processes. But it's the same kind of initiation, propagation, and termination step. Now sometimes the amount of radicals or the amount of intermediates that you have during a reaction are not constant. Maybe at every step the reactive intermediates are doubling or increasing. In such case we get an exponential growth of our radicals, and then the reaction is no longer under control. This is called a runaway reaction, and in extreme cases it may lead to an explosion, because we have to get rid of the heat and of the gas, and if there's enormous pressure buildup and enormous energy, indeed we could get an explosion. So, and a very well-known case is explosion caused by burning hydrogen. We already showed the example of the Zeppelin that exploded. And so the reaction looks innocent enough. We form water, one of the most innocent let's say, compounds that you have. But the energy that you release is enormous. And if you create it very fast, together with a very big pressure buildup, that can be dangerous. So what is happening in the initiation? Actually, a spark may be enough to create a little bit of hydrogen atoms. And now the hydrogen atoms propagate. So, and this is a simplified mechanism. But so the hydrogen actually reacts with dioxygen and forms a hydroxyl radical and an oxygen atom. Now, of course, an oxygen atom is also not very stable. It reacts with dihydrogen again and forms a hydroxide radical and a hydrogen atom. As you can see, after the second propagation step, we have already 3 radicals. And then these hydroxide radicals will propagate from water and the hydrogen radical, but again that doesn't solve our problem. So we see as a result of the propagation, we're actually going to increase and increase and increase in a very fast way our radicals. And in the end we don't have control anymore and there is an explosion. So this is a reaction that went too fast, but also sometimes reactions don't go fast enough for us. We like to increase their speed. Now, what is causing reactions to be too slow? In general, it may be because the activation energy is too high. High activation energy means a high rate constant, a lower rate constant, and so slow reaction. And well, the way to raise your rate constant is of course to raise the temperature. But raising the temperature means you have to heat, and heat costs money. And maybe also it's not convenient to heat to really, really high temperature. Some compounds might decompose and so on. So in such a way, it may be, instead of raising the temperature, we could work on the activation energy and lower that. Now how can we lower that? In such case, we have to change the mechanism of the reaction, so that it goes via another pathway which is energetically more favorable. And typically some substance is added, and this substance is called a catalyst. So the catalyst is normally something that is just helping the reaction. It's not being involved in the reaction with its atoms. It's not present in the product, so it's not used up during the reaction. It just plays a transitory role. And the result will be the lowering of the activation energy. So, if you lower the activation energy, of course, at the same temperature, there will be more collisions that are favorable to the reaction. So, let's give some examples. So, for instance, the reaction of formic acids, HCOOH, this gives CO and water. Now, it's a slow reaction, come back the next year, almost nothing will have reacted. It will still be mostly formic acid. Now, it is known that if you add a few drops of a strong acid, that this reaction goes a lot faster. And that's because of the catalysis due to this strong acid. So it's sulfuric acid here. Now you see there's actually a couple of elementary steps which are helping. Now in the first step we protonate the formic acid. And so this proton comes from the sulfuric acid, so this is the HSO4- that is forming. This protonated formic acid is a lot faster in eliminating water. You get protonated CO, and this protonated CO in the third step loses its proton, and the proton is taken up by the hydrosulfate. And we recreate the sulfuric acid. So the result of the three steps is that, well, we involved sulfuric acid, but it's back there at the end, where we invested it in the beginning. And this is a typical thing for a catalyst. So catalysis is happening a lot in chemical industry, for instance. The majority of the processes involves catalysis, but also in nature, catalysis is very important. And for instance, enzymes in nature are natural catalysts prepared from amino acids, and they can speed up reactions by really very large orders of magnitudes. So, well, I guess that is the subject of another course. Now, if you look at the reaction profile, and we're having again energy, potential energy, in function of the products or the reaction progress. So we start with the reactions, we go to the products. Now the green line is the uncatalyzed reaction. As you can see, it goes over a large energy mountain. So this is a very large activation energy, so in other words, a slow reaction. Now the red line is the one where you involve a catalyst. There might be several intermediate steps, like the example we showed before. But these intermediate steps, each of them have small activation energies, much smaller than the uncatalyzed one. So that means now we found a way to go in a faster way to the final product. What doesn't change is the energy of the reactants and the energy of the products. So we still get the same amount of energy. This is in this case an exothermic reaction if you're talking in enthalpy terms, or exotonic reaction, it will be free energy. So this is going to release the same amount of energy in a catalyzed or in an uncatalyzed way. So this is something you have to take into account. The reaction might go faster, it will also mean that the energy will be released faster. So that could be in some cases be dangerous. Very often, especially in industry, the catalysis is done in a heterogeneous way. The example with sulfuric acid that I just showed you was a homogeneous catalysis, so the sulfuric acid is dissolved in the reaction medium. If you have a heterogeneous catalyst, it's not dissolved. It's actually in another phase than the product. The products may be in the liquid phase, in the solution, and then we add a solid catalyst. And in industry, often it's also the reagent is in the gas phase, and we lead the gas phase over a solid phase. That happens quite often in industry. So, for instance, platinum is often used as a catalyst in hydrogenations. This actually, platinum helps to lower the bond energy of the dihydrogen. And catalysts, even non-chemists know about catalysts because in cars you do have catalysts. And what do they catalyze? Well, actually they catalyze the transformation of gases who are dangerous, like nitrogen oxides, the carbon monoxides, and any fuel that would not have been completely oxidized. They transform it into innocent gases like dinitrogen, CO2, and water. So, and before we had these catalysts, actually traffic was much more polluting than it was before. You had stuff like acid rain because the nitrogen oxides give not sulfuric, but nitric acid when they combine with water. The following example is one in solution. It's from inorganic chemistry. Hydrogen peroxide is normally stable as an aqueous solution. You can put it in the fridge if you want for something for bleaching, and it will remain its quality more or less. But if you add some cobalt hydroxide to it, you will see immediately gas coming out. So now we have catalyzed our reaction. And what does the cobalt do? This is in fact in two steps. So the cobalt is being oxidized in basic medium, and we get from the cobalt 2 hydroxide to the cobalt 3 hydroxides. Both are solids, so that means it's heterogeneous. Hydrogen peroxide is a solution, but the cobalt isn't. In the second step, the cobalt hydroxide is a strong oxidant, and now can oxidize quickly the hydroperoxide. Oxygen is formed, and we reform the cobalt 2 hydroxide, which can undergo the second cycle. So the result is in fact just that we speed up our reaction by, the formation of this cobalt 3 is actually a process that goes with a low activation energy. The global reaction is actually the same because in the end we didn't do anything with our cobalt. It went from cobalt 2 to 3 and then from 3 back to 2. So it just overall is hydroperoxide going to oxygen and hydroxide. Now this is what's happening in an industrial process when you're using a solid catalyst with gases. So it's a number of steps. Let's go through them one by one. It actually involves the surface of the solid catalyst. So the first step is adsorption. So the green dihydrogen or something like that absorbs to the surface. Then another reaction is approaching in the second step. The absorbed reactant is much more reactive than the non-absorbed one. So then we rearrange our electrons. There's a reaction actually which is now going with less activation energy. And then finally, of course, you have your products. And this product has to get away from the surface because we want the surface to be available for the next step. So both adsorption in the first step and desorption, removal, are important. So let's go once again. So the adsorption to the surface. So now now there's a reagent coming in. Yeah, it approaches, and now start to react. And then finally we have a product which is dissolving. I don't know if it's allowed or not. Do you have shoes like that? Okay, so there are some assignments in this chapter which we will treat in the next session, which I believe is going to be next week. So this is a more theoretical question. What are the factors that determine the reaction rate according to collision theory? I think you can revise what I have seen. The second question is also theoretical. There are a couple of statements which I would ask you to comment. The first statement says that Arrhenius constant would be the value that the rate constant would have if all of the collisions would have the right energy. The second statement says that there's a relation between the Arrhenius constant A and the orientation of the reactions during a collision, for you to consider. And then the third one is that there is a relation between this Arrhenius constant A and the entropy of reaction, and the entropy of activation, I should say. Yeah. That's cool. Here we have a couple of values for the measured initial rates of reaction between bromides in acidic medium, and we have the initial rate every time. In the table are 4 lines with 4 different concentrations, and you should see the effects, and from that determine the form of the rate equation. And maybe from that you get some information on the reaction mechanism. Then this is a question about aspirin. So aspirin is, as you know, a drug that you take against headache, for instance. So, but drugs are metabolized. That means our body is actually converting it, and it disappears from the body. This could be seen as a reaction, so we could also look at its kinetics. So, and it is known that aspirin actually breaks down in the first order reaction. And this first order reaction has a half-life of 3 hours. So it's asked to calculate how many milligrams of aspirin remains 5 hours in the body after taking a tablet that contains 200 milligrams of aspirin. So we assume it is completely taken up, it breaks down with a first order mechanism and a rate and a half-life of 3 hours. What is left after 5 hours? Okay, so that is it for the kinetics chapter. And yeah, okay. I will continue. Okay, our next chapter deals with the chemical equilibrium. For that chapter we need data both from thermodynamics and kinetics, but we will come to that in a moment. Just maybe some general information about what it means, a chemical equilibrium. So far we were mainly considering that reactions always go to completeness. So that means you have 100% conversion but this is not always the case. In fact, most reactions are not complete. So, that means there might be still some small amounts, or in some cases quite large amounts, of the reagents. And at some point the reaction doesn't go further. So these are then so-called equilibrium reactions, and this state where you have reactions together with products and it doesn't move anymore. So this state is actually called the equilibrium state. And equilibrium comes from the Latin and means equal weight. So it means we actually are keeping the balance between the products and the reagents. It doesn't mean that you have to have as much of each, but it just means that the two are keeping each other in balance and are, let's say, not moving anymore. So it doesn't mean that nothing is happening, but it just means that the products are formed as fast as they disappear to go back to the reagents. And that's what it means by the balance. So you could also call it a dynamic equilibrium. It's still moving, but the movement is as fast in one direction as in the other. So overall, it looks as if nothing is moving. So we will treat some general principles on equilibria, and in fact all of the rest of the course is about equilibria of different types of reactions, but in this chapter we treat the general principles. And mainly the reactions in the gas phase will be considered in this chapter, whereas the other chapters will be mainly about reactions in the liquid phase and in fact mainly in water. So chapter 14, for instance, is the acid-base equilibrium. Chapter 15 is the solubility and complexation equilibrium, and chapter 16 will be the redox equilibrium. Now, a bit more information about equilibrium states. So we have reached the equilibrium state when indeed there are no further changes of the composition of the reaction mixture. So there's a certain amount of reactants, there's a certain amount of products, and that's it. We can wait until as long as you want, but no further changes are going to take place. So for instance, this is a reaction which we will consider a few times. The dimerization of NO2. NO2 is a brown gas, and it can dimerize to N2O4, and we will consider this reaction at 40 degrees Celsius in a volume of 1 liter. N2O4 is colorless, so we actually can see the difference between the two gases. Now, if you look at the function of time, this should be timed, I'm sorry I use the Dutch, we can actually start from pure NO2. And then if you go in the time, you will see that it will go down, 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 but at a certain point, it will, more or less around here, it stays the same. When the NO2 is going down, the N2O4 is going up, but also here at the same moment, it has reached a plateau, a certain level, and that's it. As you can see, about this point, we have reached the equilibrium state. No further changes of reactants and products. So this is another example, I would say, in general. So as soon as you have a straight line, I think that more or less this point C here, we can say that the chemical equilibrium. And in fact, it's interesting that you can see this. The color of Na2 is brown, and this is also still brown, but a little bit less brown. So it means this bottle contains less NO2 than N2O4. And what is the difference between these two bottles? It's just a different temperature. So we also can see that the equilibrium will be influenced by the temperature. And we will come back to that later. How exactly is this dependence? So actually the bottle here on the right is colder. And at the cold temperature we have more N2O4 than NO2. Going on with this, we saw in the graph that we have a certain amount of moles of products and a certain amount of moles of reagents. We started with 100 millimole. During the reaction, actually, 37.4 mole of N2O4 is formed, and we need 2 NO2s to create 1 N2O4. So we need 2 times that amount of mole. So that means we get 25.2 mole of NO2 that is left behind, and we get 37.4 millimole of N2O4. Now, if we clearly see that the conversion is not complete. It's interesting to have some kind of measure for conversion, like a degree of conversion. And well, it can be seen that 2 times 37.4 mole is converted, so that's actually 74.8 mole of the original 100 mole that are converted. So we could say the degree of conversion is 74.8%. Or if you express it as a number, it's 0.748. So meaning it's not 100%, but it's close to it. 3/4 of the product has been converted. This is what I already told. The equilibrium is dynamic. So in fact, N2O4 is falling apart as fast as it falls. And this keeps the reaction in equilibrium. So the value of conversion, if we express it as a number, it can be between 0 and 1. We can also say percentage of conversion, and then we have to multiply it with 100. So if it's percentage, it was 74.8 in this case. Now, this is normally expressed by alpha. So alpha is a degree of conversion, and then that's a number between 1 and 0. So we can also express degrees of conversion for different reactions, like degree of ionization, degree of hydrolysis, and so on. Sometimes the Greek letter then changes, so it becomes gamma or something like that. It's still degree of conversion. Now, there is another way to express how far is the reaction going. And so, to what extent is the reaction proceeding? And that's the equilibrium constant. This is expressed by K, but now capital K. So don't make the confusion with small k, which is a rate constant. How do we express the equilibrium constants? It's actually something that you can get from the reaction equation. typical reaction equation, you have two reactants, R and S. They have coefficients, small r, small s. They are in equilibrium, and we use these kind of arrow to show that it's in equilibrium. They're in equilibrium with two products, x and y. X has a coefficient x, y has a coefficient y. Now K is actually a ratio of concentrations. In the upper parts of the ratio are the products, and they have exponents, which is the coefficient of the product. These are divided by the concentrations of the reagents, and again, exponent is the coefficient. That might be. So in many cases, the coefficient is 1, that we don't have to put anything. But sometimes there are 2, and there are 3, and so on. Reagents or products, then we have to square it or cube it in our equilibrium constants. The concentrations are expressed in mole per liter, so in molarities. And these are the concentrations at equilibrium. So we have to make sure that the reaction got the time to reach the equilibrium. In that case, we can determine K from the measured concentration at that equilibrium. And this K tells us something about the reaction. If K is 1 or larger than 1, maybe sometimes a lot larger than 1, this means a reaction that is mainly going to the product. It is to the right. If it is smaller than 1, actually there is very few conversion for such a reaction, and you have mainly still reactants. Some Ks are really, really very small, like 10 to the minus 10. In such case, you know there's very, very little conversion. And products will be formed only in minute concentration. So, for the K, for the reaction that we just studied, the dimerization of NO2, this becomes, the product is N2O4, the concentration of N2O4 is put there, and the concentration of NO2 is squared, because we needed 2 NO2s as reagent. So we know the concentrations, so let's put it in the equation for the equilibrium constants. If we do that, we see that Kc at 40 degrees, and you have to tell the temperature because K is temperature dependent, is 58.9. Now I put Kc, and the C is for concentration, because this is an equilibrium constant based on concentrations. As we will see, there are other possibilities with gases to express an equilibrium constant. So the dissociation reaction is actually the opposite. We start from N2O4 and we go to 2 molecules of NO2. So that means we interchange products and reagents. That means the new K of that reaction is 1 over K of the dimerization reaction. Because we have just interchanged the part that is up on the ratio with the one that is down on the ratio. So that means we could calculate again, but in fact we could just also say 1 over 58.9. And then we arrive at 0.017. So this is a small k, so that means that dissociation is actually not a very favorable reaction. And so there's actually a little is dissociating of your material at 40 degrees. The unit of K is normally not mentioned. It actually depends on how the reaction equation is and how much concentration terms you have. So this is about reaction in the gas phase. We could now express, instead of with concentrations, we could express with pressures of gas, partial pressures, in fact. We have a gas mixture. Each gas product, reagent, will have a partial pressure, and we now put these inside of our equation. Then we will get a new kind of equilibrium constant, Kp, based on the partial pressures at equilibrium and at a certain temperature. So for the rest, it's exactly the same kind of format. Now, Kp and Kc, are they not related? Of course, they are related to each other, because concentration and pressure is also related. So you can in fact say that, so you know PV is nRT, and N over V is the concentration. So that means Px is the concentration multiplied by the factor RT. And that means actually Kp is the concentration equilibrium constant multiplied by RT to the power delta N. Delta N, the amount of extra mole that is formed. And so if it means if there are 3 mole of products and 2 mole of starting materials, then delta N is 1. It could be the opposite, that you have a negative number there, you have less product than you started with the starting material, then it's minus 1. It could also be that it is the same. As many moles of gas are formed than you started from. In that case, the delta N is 0. That means that Kp is Kc in that case. That both equilibrium constants will be the same. So for instance, we have an example here. The oxidation of dinitrogen to NO. 2 moles give 2 moles. Delta N is 0 and Kc is Kp. RT, we have to, this is a PV nRT formula that we're using, and P was in atmosphere, so that means R has to be 0.082. And the temperature, of course, is as usual in Kelvin. So that actually means that for the dimerization of NO2, this example that we have, and this would be 1 liter volume at 40 degrees Celsius. So we have an equilibrium state with a partial pressure of NO2 of 0.647 atmosphere and N2 of 960 atmosphere. So then we can put this in our Kp expression, and so that's 2.29. But we could also have calculated that from Kc by dividing by RT, because you see that we actually are losing 1 mole of gas in the dimerization. So delta N is minus 1, so that means we divide by RT. So we divide by 0.081 and 313, that's 40 degrees Celsius. And then you also arrive at 2.29. Okay, so I think we'll have a small break before we start on heterogeneous usual, I'm available if there are questions.
Can you
cái đây không phải cái này là bách khoa với mình nhảy phát
Okay, let's start again with the course equilibrium. I received more questions, always interesting to discuss it. So first of all, somebody asked from the previous chapter, does zero order also exist? Yes, it does exist. In some handbooks they discuss indeed zero order, but we are not going to discuss it during this course. It's maybe a little bit more advanced subject, but zero order can happen, for instance, when you have a catalyst which is saturated, and then the rate is independent of any of the concentrations. So then the bottleneck is the amount of surface that is available, and that's going to control your reaction. But then this is zero order, because you cannot look at it in, let's say, some kind of concentration. And the same in biology, enzyme reactions are also zero order, because mostly the enzyme is saturated. So that is also one example. But I would say, don't consider this as part of the general chemistry course. Maybe also for this part I went a little bit too fast. This X that you see between brackets is a concentration of any compound, and the concentration can be seen as N over V. And then delta N is just the overall difference in amount of mole of gas. Okay, about heterogeneous equilibria. So gas, solid, liquid, solid. Here we have a reaction we have already seen several times. Calcium carbonate decomposing to calcium oxide and CO2. Now, you have to consider these as a reaction with gases. That's one phase. And in fact, only CO2 is a gas. So that means if we now make Kp for this reaction, it's actually very simple. CO2 is a product, there is no coefficient, so the Kp is the pressure of CO2, nothing else, that's it. Kc is the concentration of CO2. So, what about calcium carbonate and calcium oxides? Well, these are solids. And solids do not have a changeable concentration. They're condensed phases. So both for solids, also for liquids. If they are in such an equation, we don't have to count them. So this is not a variable concentration. So that means only one term. This becomes a very simple reaction equilibrium constant. Equilibrium constant. So to give another example where there is a heterogeneous equilibrium, and we'll treat it much more in the chapter 15. That's the solubility equilibrium. A poorly soluble compound like silver chloride is splitting partially into silver cation and chloride anion. And now you have a KSP solubility product, and this is only made from the concentrations of silver plus and chloride minus. Silver chloride is not there. Why? It's in another phase. It's solid, and the solid is not changing its concentration. So liquids, same story. So here we have the dissociation of water to dihydrogen and oxygen, and this Kc is in fact concentration of hydrogen squared multiplied with oxygen. No H2O. Because this is the liquid phase, and in the liquid phase it's always the same concentration. It's constant. So here again this becomes important to consider the aggregation states of the water. It could be that you do the same reaction but starting with water vapor. Now this reaction with water vapor will have a different equilibrium constant. Because in the water vapor we have to consider also the term of the water as reagent. So we have to divide by water concentration squared, or if it's Kp, by the partial pressure of water squared. So how to calculate equilibrium constants? Of course we need concentrations for that. So this we can do in simple matter. Here we have an example with a kind of exercise, you can say. So we start from 100 millimole of phosphorus pentachloride. It is heated to 500 Kelvin, and it partially decomposes. So the phosphorus pentachloride releases dichlorine, and phosphorus trichloride is staying behind. And at this temperature, 500 Kelvin, actually all of the components, products and reagents are gases. So the volume of the gas mixture is 5 liter. This is the equilibrium mixture, and the pressure within the reactor is 1.26 atmosphere. So we have to calculate now what are the values of the equilibrium constants Kc and Kp. So how do we start? The good start always is to write the reaction equation, which is quite simple. In this case, it is given that we started with 100 millimole, and actually there is a certain amount, at the moment we don't know, so we are now going to use an algebraic way of doing that. So how much is going to disappear? Well, X of PCO5. You don't know? It means we will form X mole of PCO3, the same amount, and we will form the same amount of dichloride. So these are the concentrations. 100 millimole minus the X mole, and there is X mole formed for both PCO3 and CO2. So the total amount of gas after the reaction is 100 millimole plus X mole. Why plus X mole? We have here minus X mole plus X mole, so that's again 100, but we have also the chlorine extra. So we have more gas before than after. So we can actually determine the X from that with the gas wall. PV nRT, that means N is PV divided by RT. And we have all the data. The pressure was 1.26 atmosphere. The volume was 5 liters. And we divide by R and T. 500 Kelvin, R is 0.08. So that means we actually get not hundreds, but 154 millimole of gas after the reaction. That means X is 54 millimole. That's the amount of chlorine and the amount of PCO3 that is formed. So we know already a lot more now. We can fill it in. 54, 54, 46. Is this going to be? So we know all of the amount of mole that we have. And we know it's in 5 liter. So we can now actually calculate this. Kc is actually 0.013. So this is how we calculate the concentrations. We divide every time the amount of mole by the amount of liter. And Kp we can also calculate from the partial pressures, but also we could convert Kc to Kp. And you can see Kp is 0.51. The pressures are calculated in the expected way. So we can actually go in the reverse way. If we have K, we can calculate the concentrations of an equilibrium mixture. So suppose we now have NO2. Okay, and for NO2 we earlier already calculated Kc and Kp in the beginning of this class. So we bring it now into a volume of 10 liter at the same temperature, so K remains the same, 40 degrees Celsius. So we knew already that Kc was 58.9. That's we had calculated. So now I would like to know how much mole of N2O4 would have to be formed under these conditions. Again, we can solve this algebraically. So the conversion is set to be a volume X, or in fact the amount that we form. Here is X. That means actually 2X. Mole of NO2 would have to disappear. And so that means the 100 mole is going to be afterwards diminished by an amount of 2X. So now we can put this in the equation. So it's in 10 liter. X is the amount of moles, so we divide X by 10 to get the concentration of the N2O4. So the NO2 is 100 minus 2x, also divided by 10, but squared. If we solve this equation, we can get the result, and this is 0.020. So 20 millimole is actually being formed, and that means a concentration of the NO2 that is left is going to be 60 millimole, because we have to subtract 2x from that. So as you can see, we have expanded this now to 10 liter, and this has an effect on the equilibrium. So, of course, solving this kind of equation may not be so simple. So in some cases you get quadratic and other equations. Luckily, very often we can make simplifications. If we assume that x is small as compared to the number that we have actually subtracted from, then we can in some cases just omit x, and then it becomes a lot more simple. Of course, we have to check afterwards if our assumption is correct, that x was small enough to simplify. So here we have a reaction. It's in fact an oxidation of NO2 with oxygen to N, with NO with oxygen to NO2. And we know that it actually has a low conversion. We have 10 millimoles of each, and we know that, sorry, it's not a low conversion, it's a very high conversion, excuse me. How do we know it? From the data that is shown here, Kc, 5.5, 10 to the 13th. That's an extremely large number, this. So that's 55 billion. So what do I say? Trillion, actually. 55 trillion. So that means it's only products. Only very, 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 very little of the starting material is left. So now you have to choose your parameter x carefully. So you choose it that this x is the amount that is left. And now we know that, okay, we will be able to make simplification with this type of x. So that means to have left only this very small amount of x, we have to subtract 10 millimole from the original 10 millimole, except for that small amount, x. And then everything else follows from that. So half of it has to disappear in oxygen, and the same amount is now forming, so meaning 10 millimole, except for that very small amount x. And these then become the concentrations at the end when the equilibrium is reached. So now we put that in our equation. We have the number for K. Yeah. So NO2 is the product. This is the concentration. It's in 2 liters, so we divide by 2. It's squared because there are 2 NO2 molecules. There are also 2 NOs. There's X amount NO left, divided by 2 liters. And this is the amount of oxygen that we have to use up. We are not squaring that because it's only 1 mole. So this would be a quite complicated thing to solve without simplification. So what can we simplify? We know that x is very small compared to 10 millimole. So let's drop it. This x, of course, we cannot drop. We have to keep that to solve it. But also we know that half an x will be small compared to 5 millimeter. So we also drop that. So then these become simple figures, which we can move to the other side. And now it just actually we have to make the square root of all the rest. So it becomes very simple. And if you solve that, indeed x is 2.8 10 to the minus 8. So that's an extremely small number if you compare it to, let's say, 10 to the third or 10 to the second. And so that's 6 orders of magnitude. So that's like 1 part in a million. So that means you can certainly simplify it. So there was no problem to do that. So now I want to talk to you about the reaction quotients. So, this is with another letter, Q, not K, but it has exactly the same form as K. What is the difference between K and Q is that the concentrations are not the concentrations at equilibrium, but the concentrations at the moment when we add everything together, at the beginning of the reaction. And this actually tells us something on the direction that the reaction will take. So we can compare K with Q. Now, if Q is actually smaller than K, that means the products are not in balance with the reagents, and it wants to restore that balance, go towards K, and that means the reaction will shift in the direction of the reaction products. If, on the other hand, Q would be larger, then we move in the direction of the reagents. So let's again look at a real example, again with this equilibrium between PCO5, PCO3 and chlorine. So let's put 0.2 mole of each in 1 liter at 500 Kelvin. We know the equilibrium constant there, and it's 0.013. So for Kc. So as we have calculated earlier. So in which direction will this move? So Q is then the ratio of all of the concentrations. And in fact, all of these are 0.2 mole in 1 liter. So they're actually 0.2 mole in 1 liter. Yeah, okay, then this should be without 0, I think, 0.2. So all of the concentrations are the same. It's 0.2, 0.2, 0.2 in 1 liter. So we divide 1.2 to the other. It's finished. So 1 is left, 0.2. So this 0 disappears. That means now this number, 0.2 without 0, is larger than 0.013. So that means also this Q is larger, so we are moving towards the reagents. So we are actually going to form more PCO3 and chloride. So the extra amount of PCO5 can be calculated in this way, and it's going to be 2.8 10 to the minus 3. But that calculation I will leave for you. So equilibrium constants are also in relations, have relations to each other. Like a very simple one is that if we invert the reaction and we change reagents and products, the products become the reagents and the reagents become the products. So that means we invert the arrow. Then it's actually the equilibrium constants becomes a reciprocal, the inverse. That's logical because this is a ratio which now A over B becomes B over A. So we can also combine equilibrium constants mathematically with each other, like we have done before for thermodynamic things. We can combine them in the same way, but it's not exactly transitive. So that means if a third reaction that we're considering is the sum of two reactions, the equilibrium constant is not the sum, but the product of the two. So we have K1, K2, we have the K1 multiplied by K2. If actually the third reaction is the difference of the two other reactions, we have the third equilibrium constant, which is the ratio of the two. Now, if there are any coefficients, so for instance, you have reaction 1 minus 2 times reaction 2, then we have to square the K of the reaction. So we have to put the exponent according to the coefficient. So here we have a number of simple reactions of carbon and oxygen, or CO and oxygen. So they're simple equilibrium. It can be shown that we can get reaction 3 and 4 by combining reactions 1 and 2. So it is actually, the third one is the difference between the two reactions, and the fourth one is the difference between 2 and 1. But we have to take 2 times reaction therapy. What does it now mean for the equilibrium constant? So we look at the terms in concentration terms. So the third one is CO square divided by CO2 concentration. And now we divide each part by the oxygen concentration. And then you can see we actually can make 2 new concentrations, so 2 new equilibrium constants, K1 and K2 in concentration terms. And you can see this actually agrees with the fact that reaction 1 minus reaction 2 is the third reaction. What about the fourth reaction this is the expression for the equilibrium constant. We divide everything by the oxygen square, by oxygen square. So that means here we have oxygen square. Here we have already oxygen, we divide by oxygen square. So one of the oxygens drops, so we have this. And now you can see that this is nothing else than the second reaction, but squared, and this is the first reaction. So this agrees with the 2 times the second reaction minus the first reaction. By the way, you see in none of these equilibrium constants we have carbon, even though carbon is mentioned in the reaction equation, but carbon is a solid. And so we have a heterogeneous equilibrium and the concentration of the carbon is constant. So that is why it is not mentioned here. In the beginning of this talk I had discussed degrees of conversion, normally expressed by alpha. There's actually a relation general qualitative, we can say, if you have high degree of conversion, you also have high K. But you can calculate exactly how much by establishing the relation of, between K and alpha. The thing is, it's a different relation depending on the form of the equation. So there is no general formula. You have to look from case to case. So here, for instance, we have a dissociation reaction. Two groups X are connected to each other and they fall apart. X could be a halogen or could be anything. So before the reaction we have a certain concentration of X2. After the reaction we will have 1 minus alpha left of that concentration, with alpha being the degree of conversion. So if you have 70% degree of conversion, there's 25% left. 100 minus 75. So how much mole is being formed? In fact, the double, because for every X2 we have 2 times X. So we have two concentration multiplied by alpha. So we can fill that in. 2 alpha concentration we have to square. So that becomes 4 alpha square concentration square. And then the concentration is 1 minus alpha C for the reagent. So we can drop C here. We drop the square. And so now we have our conversion for this type of reaction, which is 4 alpha square 1 minus alpha multiplied by the concentration. So you see here, this is concentration dependent, this conversion. So this not always has to be concentration dependent. Here we have an example where it isn't. This is for the reaction of a weak acid with water. Partially, the weak acid, HA, gives its proton to the water. This is something that we will look at in detail in the next chapter. Now, you can do the same. So, the concentration of water is not important, it's a liquid, it doesn't change. So only the concentration of HA is important. After the reaction we have 1 minus alpha of the concentration of HA. Alpha A minus is formed and alpha H3O plus. So now we see what we get is alpha square concentration over 1 minus alpha. So that's the way to convert it. Here we have a kind of interchange of 2 groups X and Y. We have a heteronuclear compound, 2XY, going to X2 and forming also Y2. Again, after the reaction, 1 minus alpha concentration. Then that means we get half of that formed, half of the alpha concentration. So we can put everything here. As you can see now, the concentration terms cancel each other. We have concentration square, so all of the terms that have concentration are dropping out. And what we now have is alpha square divided by 4 times 1 minus alpha square for the conversion. So in this case, we will not have a dependence on the initial concentration of XY. Okay, so I think we will have another break. So if you have any questions, please come forwards, and then we'll continue with the thermodynamic approach to the equilibrium. Okay, let's continue with our treatment of the part of chemical equilibrium. So it can be shown that when you have differences in pressure of concentrations, that this can be also related to a free energy difference. And so you could actually say that delta G is nRT of the natural logarithm over the ratio between the pressure at the end and the pressure in the beginning. So, and well, we could consider that this could be also at standard conditions. So that means 1 atmosphere of pressure for the gas, and when it's different than the standard conditions, actually that means we have to add the RT over P ends P of the 1 atmosphere. So we have to divide by 1, but of course that remains in LNP. For dissolved compounds, we are at molar concentrations. So we can then write it as concentration instead of like pressure. So it becomes pretty much the same. So the N is no longer there because it's already in the concentration term. So of course we know that the concentrations or the pressures will change during the reaction. And this can be related now to a change in the free energy. And for instance here we have the composition of a mixture, and this is related now in the curve to its free energy. So what you see here in the x-axis is the chemical composition, meaning the fraction of one compound versus the fraction of the other. And this is for the dimerization of NO2 that we already studied. So that means the situation over here has no NO2 and only N2O4. The situation over here has only NO2, no N2O4. And this is anything in between. This is more or less half-half. And you can see the minimum of the energy, or the free energy, is actually where we have the equilibrium mixture. So that means the mixture spontaneously evolves to the more stable equilibrium mixture. And in this equilibrium mixture we have the two compounds together in a certain ratio, which is the ratio that we also find in the equilibrium. So we knew already from earlier work that these are the concentrations of N2O4 and NO2 in the reaction mixture at 40 degrees and 1 atmosphere. So important to realize that the minimum of the free energy in the graph corresponds to the equilibrium state. So we can actually say that the free energy of the mixture is composed of the free energies of the two components, reactants and products, multiplied by the amount of mole that we have of each. So how can we express this more in terms of the different reagents and products? So we now can say that we have a delta G, which is equal to the delta G at standard conditions for the reaction, plus a term RT of the pressure of the products, N2O4, divided by the pressure of the reagents. It's squared, because there are two of them. So this is actually derived from the fact that we will have the same for the free energies. So it's free energy of the N2O4 minus 2 times, because we have 2 molecules of NO2, the free energy of the NO2. So we can derive it from that if we combine the expressions like we have seen before. Delta G, here we have it. G is G0 RT ln concentration, or ln P when it's actually a gas. So here we have combined. So if we look at it as kind of Hess diagram, so say that, okay, in the beginning we have 2 mole of NO2. This has a pressure, which is the partial pressure of NO2. So at 1 atmosphere, which is the standard condition, it could move to another pressure, which is not 1 atmosphere. This is the factor then that we need to add to go from the standard pressure to the whatever pressure it is. So if now we do the reaction and we go from 2 mole to 1 mole of N2O4, this has a certain pressure. Also here we could look at the situation at standard condition and make the difference according to this formula. So, this is in fact how we then can come to this if we add up all of the free energies and we combine their logarithms. In fact, we could say for any reaction, this is the equation that we can use. Delta G at any kind of condition, concentration and pressure is delta G under standard condition plus the term RT multiplied by ln Q. And Q is, as you know, the expression in the same form as the same form as the equilibrium constants, but not necessarily equilibrium concentrations. This might be the initial concentrations. This is a reaction quotient. So delta G might be positive or negative. Now we can show that if delta G is negative, as we know, it's a spontaneous reaction. That means the reaction is going forwards towards the product. If, on the other hand, delta G would be positive for certain values of Q, and these we can calculate based on the data that we get, then the reaction would go in the reverse order. That means it's actually going towards the reagents. And this brings us to a thermodynamic expression of the equilibrium constant. So now we apply this equation that we just saw with the LNQ to an equilibrium situation. Now at the equilibrium, in fact, there is no more change of free energy. We stay fixed in one position. So we can say that delta G is going to be 0 at equilibrium. And we also know that the general expression is delta G standard plus RT and then LNQ. Now we fill in the concentrations, and these are equilibrium concentrations. So it's no longer LNQ, but it's LNK. So, in other words, it means delta G standard plus RT LNQ, LNK, is 0. Or, in other words, delta G is minus RT LNK. And for gases, it's LNKP. For reactions in liquids, it's LNKQ. So, this is one of the most important, I would say, expressions in this chapter, and it gives a direct, let's say, relation, which is logarithmic, between the free energy and the equilibrium constant. If you have one, we can calculate the other if we have also the temperature. Now, again, this is in the x-axis composition, meaning either complete products or complete reagents. So, and here you can see how free energy could be evolving depending on the size of the standard free energy of the reaction. So here we have a negative free energy of reaction. We know this is a spontaneous reaction. That means it occurs and moves towards the products. That means the equilibrium state will be more to the products. Here we have a delta G of 0. It's not positive, it's not negative. So that means equilibrium mixture, we are more or less at 50-50 of all of the products. In fact, if all the concentrations are 1 atmosphere, 1, 1, 1, you divide by 1, it's still 1. So that is what you would expect. And so we have the K is 1, the logarithm of 1 is 0. That's what you have here. So this is a positive delta G. And we know that the positive delta G is a non-spontaneous reaction. So this is not going to go very far. And that means we will mainly still have the starting materials and not a lot of products. In fact, you see, if you form more and more products, you actually go up in free energy. That's not good. You want to go down as much as possible. Now we can also look at the previous chapter, kinetics, and see, okay, is there any relation between the kinetics and the equilibrium? And I can tell you that there is. Because the equilibrium is dynamic. So we have two reactions going on at the same time, and they keep each other in balance, in equilibrium. And you could define a speed going from the left to the right, reactions to products, and a speed going from the right to the left, products to reagents. And in fact, these two, when we have reached equilibrium, keep each other in equilibrium, so the two speeds are actually the same at that moment. Now, it's interesting to see that you could consider that the dimerization of NO2 is a second order reaction, and dependent on the concentration of NO2. And there's a K, which is needed there. So K left to right. Here we have K right to left. N2O4 is actually first order. So the two speeds are going to be equal to each other at equilibrium. So that now means we can bring the K's all to the same side. And now actually we make the ratio of K up and go K down. And we also at the same time make the ratio of the concentration at equilibrium. And as you can see, this expression is nothing else than the concentration dependent equilibrium constant. So here we now see the relation between small k and capital K. It's actually the ratio between the two constants, rate constants, makes the equilibrium constant. If both of them have an equal K, it would mean big K, capital K, equilibrium constant is 1. And this is a perfectly matched reaction. We're about 50-50 between products and reagents. This now is true only for elementary reactions, because normally there is no direct connection, of course, between the form of the reaction and the kinetics of the reaction. Because there might be a totally different order of reaction than you have actually in your global reaction. But you see the point that we actually have the ratio between the rate determining steps. Now, we are actually faced with these equilibrium mixtures. And we could say this is actually not very good, very advantageous. We would like to push our reaction to one side. And how can we change that? How can we fix this problem? But luckily the chemist has a possibility to displace the equilibrium to the side that we want by putting some kind of outside influence. And this answers to the so-called principle of the Chatelier, French researcher of, I think, the 18th century. So it says when you change one of the factors, temperature, concentration, pressure, in the system in equilibrium, now the equilibrium will shift. And it will shift in such a way that the equilibrium shifts back to the original situation. So it tries to undo the change that you have applied. And now we can look at several situations. Now, for instance, what happens when we increase the temperature? Now it depends on your reaction. Your reaction might be exothermic or endothermic. So delta H larger than 0, that's endothermic. This is exothermic. Now if you heat your endothermic reaction, the endothermic means you take in energy. So the energy that you have taken in by the heating, you can actually use for the advancement of the reaction. So that means your equilibrium shifts to the products. So if you want that, that's good. Endothermic reactions you have to heat if you want more product. K is going to increase as an effect of this temperature change. Now for an exothermic reaction, and you want more product, it's not a good idea to heat. You should actually cool it. If you heat it, your K will decrease, and that means you go more into the direction of the starting material, of the reagents. So, concentration of the reagents. So suppose we have an equilibrium mixture, and we add more reagents. So how can you counteract that? Is by taking away a reagent, and this happens when you form more product. So that means your equilibrium moves towards the products. However, your K is not changing. This is just an effect of the concentration increase that you have. Your K only changes when your temperature is changing. Otherwise, it's a constant. That's what means constant. If you add your products, the way how to resist this is by taking away products, and that means you move to the starting materials, to the reagents. So that may not be a good idea if what you want is product. What about pressure? Now pressure has only, of course, effects when there are gases involved. And now it depends on the amount of gas before and after reaction. So we look again at delta N. So if you have an increase of gas moles in the product, delta N is positive. If we take away gas, the delta N is negative. But it's also possible that there is no change. of moles of gas. So suppose we increase our amount of gas and we put pressure. That's actually not good, because the additional gas will create more pressure, so we go against. So how can we escape? We move to the side where we have less gas. That means to the side of the reagents. So if we want to have a positive effect, we should take a reaction where actually we go to less amount of gas, then actually putting pressure on it will have a positive effect, and we move to the products. Now, if you go from 2 mole of gas to 2 mole of gas, so no change, you can put all the pressure you want, but it's not going to make any difference, because only the reactions that have differences will be affected by increases of pressure. In all of these cases, since we do nothing with the temperature, we don't expect any changes to our equilibrium constant. So let's look a little bit more in detail, more quantitatively, to what is the influence of the temperature. We look at the thermodynamic expression for the free energy. So we can split the free energy term into an enthalpy and to an entropy term, so delta H minus T delta S, under standard conditions. So, what we see here is that this term here is independent of temperature, whereas this term has a temperature dependent term, and it's also the one that has the enthalpy. So this actually explains now this principle of the Chatelier, why exothermic reaction, if you heat, you go to the starting materials, and endothermic, you go to the products. We can also write this as an LNK. So, this expression, you might be reminded from the expression we also have for the kinetics with small k. With a small k, we have the same ln small k1 over k2, but then delta H was activation temperature. So it's exactly the same. So that means if we know one of the equilibrium constants at a certain temperature, T1, and we go to a second temperature, T2, that we know, and we know the enthalpy, then we can calculate what is the second equilibrium constant. Or otherwise, if you have two different equilibrium constants at two different temperatures, then we can calculate the enthalpy. That would be another way to do it. You can also look at graphs of the free energy, of the LNK, in function of 1 over T. So, as expected, it is linear, but the slope will go down or will go up, depending on the case. And the slope now is minus delta H over R. So it now depends on is your reaction endothermic or exothermic. So on the left case we have an endothermic reaction, meaning delta H is positive. So that means minus delta H over R is negative. So that means now your reaction is going down, but it's 1 over T. So that means this is the region of low temperatures, this is the region of high temperatures. So you see, at high temperatures, we actually have a high LNK and we also have a high K. So that shows that the endothermic reaction, when you heat it up, you go to higher temperatures, we actually get K increase and we move to the products. Exothermic reaction, same thing, but now delta H is negative. Minus delta H over R is positive. That means our line is going up. That means at the high temperature now, we actually have a low LNK and we have a low K. That means at high temperature we move towards the reagents. So this is LNK, but small k. So this is the rate constant. And we can also write relation to 1 over t in the same way. You remember the Arrhenius law, so which says K is A multiplied by E over activation energy divided by RT. So depending on the activation energy, which is also always positive, so that means we get curves which are going down in any case. The difference is now how fast does it go down. And how fast does it go down depends actually on the activation energy. So, with high activation energy, you actually have curves that go down faster. Now, the large K, capital K, equilibrium constant, is the ratio of these two. So what we see here is an endothermic reaction. And in the endothermic reaction, actually your K of going from the left to the right is with a higher activation energy. And you have to imagine the graph of delta G versus reaction coordinates, and you will see indeed the activation energy is larger for the reaction up than for the reaction down. And so this is the reaction down. So this is winning. This is the reaction that is winning, especially at higher temperature. This is the opposite, when we have an exothermic reaction. Now the activation energy for the reaction back is the one that is the largest. So this is the one that is going that fast. This is a little bit less. So K will be larger than 1 in this case. So indeed, the logarithmic form of the Arrhenius equation is ln K is ln A over minus EA R over T. So minus EA over R is the slope of the reaction. Now, suppose we shift our reaction, but we keep the temperature constant. That means also K is a constant. That's one thing we don't have to worry about. It's not going to change as long as we don't change the temperature. So, if we change the concentration, Le Chatelier actually says that we will move to the direction where this concentration will disappear. So, reagents shift to products. If we add products, shift to reagents. So this is something that we will encounter in one of the next chapters when we will talk about the solubility equilibrium. So suppose we have the precipitation reaction of lead chlorides by combining lead cation and 2 chlorides. So this now, if we add chlorides, but in the form of sodium chloride, you will actually precipitate more of the lead chloride. And this is to take away this chloride. So here, for instance, this is an equilibrium reaction, the one between calcium carbonate, calcium oxide, and CO2. So it will stop after some time. But we could allow the CO2 to escape from the reaction vessel. If we do that, well, Le Chatelier is saying we will make more CO2. And the only way we can do that is to push the reaction completely to the right. This is one way to make the reaction complete. We just take away the CO2 the whole time. And then more and more will fall until it is finished. What about change of pressure? Well, we already treated that, so we move into the direction where there are less gas molecules when we increase the pressure. Here we have an example with again NO2 and NO4. So we have the equilibrium concentrations of 25.2 mole NO2 and 37.4 moles N2O4. Again at 40 degrees, so the same temperature, we keep K, and the volume is again 1 liter. So now we expand to a pressure of 1 atmosphere. So that means the volume has to change. To do that. Because the original pressure was, I think, 1.26 or something. So we have to calculate the amount of mole of the gases and the volume at this new equilibrium, so at the lower pressure. So we have to take first the gas law. As you know, it's PV and RT. From that, it follows that the original pressure should be 1.61 atmosphere. We calculate that from the N, the amount of gas. The R and the T is known, and also the pressure we have to calculate. The volume was 1 liter. So Kp we knew. Kp was 2.29. This was calculated before. So now again we have to solve it algebraically. We think there's going to be formed a small amounts of X. We can actually make this with simplifications probably. That means the amount that changes X, the small amount. So 2 times that amount of NO2 has to disappear, and these are then the concentrations afterwards. So with the Kp, we are actually putting these concentrations here. We know it's 2.29. These are the concentrations, the pressures that we are having. So the total pressure is 1 atmosphere. And what we have here is the mole fraction. So that's the partial pressure of the N2O4. So this here is the total amount of moles that we're having. And this can be calculated by adding up this and this. And we put this as the amount of mole of N2O4. Now X is small, so we can probably simplify this in a way. So then it is also possible to do the same here. And so from this we can actually calculate X. We can see that X is going to be 3 millimole, so only relatively small. The part is going to shift. So the volume now is 1.69 liter. And this we can calculate by putting X in this, and then using the gas law again. So we can see now the original volume of 1 liter had to expand to 1.69 to accommodate this amount. Okay, so there's a couple of assignments. We will treat them, I guess it will be next week. So, because this is, I think, the last session for this week for this group. So this is something that is actually more like an acid-base equilibrium, but still you are going to look at in terms of general. So acetates transforms into acetic acids. Okay, sorry, this I should correct. So acetic acids. Yeah, yes, no, it's correct. To acetic acids. So the solution is 100 millimolar sodium acetate. But the conversion alpha of the acetate is 7.5 10 to the minus 5 at 25 degrees. So it's asked to calculate K, the equilibrium constant. So you should first make the conversion factor formula and then apply it. So, then for the second one, we should calculate the values of equilibrium constants Kp and Kc. And at two different temperatures, 25 degrees and 1000 degrees. Now, in order to do that, we have to use the formula ln K is minus delta G is minus RT ln K. And then that means we need the free energy. And to calculate the free energy, it's a thermodynamic calculation, so you will need your table 4. To calculate delta H, delta S, and then the two temperatures, to calculate the two free energies, and then from the two free energies you can calculate your K. Kp and Kc can be derived from each other by multiplying with the right factor of RT over delta N. And there are two exercises more, which you can also, if you have the time, have a look at. The first one is the reaction of methane and water. So we convert to CO and dihydrogen. That's again the syngas reaction. And so we did earlier already some calculations on it. But now we look from the viewpoint of equilibrium. So at which temperature will Kb be 0? Not 0, 1. Will Kp be 1? So will there be a perfect equilibrium, in other words? What is the influence of an increase of the temperature? So we have to apply the law of the Chatelier to this. So is this going to raise or lower the K? So, and what does this do with the total pressure on the molar fraction of the hydrogen? So, then we discuss also the influence of the increase of pressure on constant temperature on the molar fraction of the hydrogen. If we increase the pressure, will we have more dihydrogen or less? Then the conditions needed to have reaction with gaseous reagents and gaseous products, and you have to look at each of the conditions separately. So what is needed so that the Kp would increase when you have an increase in temperature? What is needed for a value of delta G to increase when the temperature increases? What is needed for the value of K? And now we are looking wish you a pleasant weekend. So, and we see each other next week. I will remain here for a couple of minutes if you have any questions remain.